Well, greetings, mathletes, and welcome back. So, we are still talking about graphing sine and cosine functions today. In fact, we may very well have one more lecture on it too. So, we're still in the same section as the last section. What we covered this last time is how to affect the amplitude of a function. Um, but there's a lot more you can affect as far as sine and cosine go. You can change the period. You can shift it from side to side, or you can shift it up and down, right? Or any combination of those things. Changing the period is essentially stretching or compressing it. Changing the amplitude is stretching it or compressing it, but in a different direction. And then um, everything else is just shifting left, right, or up and down. And so we just need to know how to read those things and how to calculate where the curve has moved or how the curve has changed. So just so you kind of have a visual on what we're doing here, I've gone ahead and made a little display here so we can kind of get an idea. This is a sine curve, and let me just go ahead and jot something down here too. This is the function f of x, I used x just because we already have an x-axis, is equal to, come on, right? There you go. A times, this thing is not that good. Ay, ay, ay. Why is this having so many issues? Okay, that is not, you know what? I'm just going to do it this way. Hang on a second here. Um, turn that back off. Let's just type it. Okay, so the function is f of x is equal to a sine bx plus c plus d. Okay, so we're looking at that. Let's see if we can adjust the font here. I don't know if I can adjust the font. Let's see. No, I can't. Okay, but in any case, okay, that was a little weird. I thought that would be a better display. In any case, that's the form of the function. And what I've done is I've entered the x coordinate of these points as these values. So if I want to affect a, we know a is the amplitude. We can see what happens as I change that number a. So right now a is 1. If I stretch it this way, we can see the curve stretches out. I can go all the way up to 3. And you notice the amplitude is 3. And then we can see what happens too. As I get closer to 0, the curve flattens out until it is flat. And then when you go negative, it reverses the curve. So you can kind of see how the amplitude changes on the curve when you change the value in the function. Now, changing b changes your period. And we'll talk about how to get these things out with a direct numerical computation in a minute, but I'm just kind of giving you a feel for what these things look like. So b changes the period. Now, counterintuitively, if you make b bigger, the period gets smaller. So watch what happens as I move b to the right. You notice the thing shrinks. It pushes up towards the y-axis. The bigger b gets. The closer b gets to 0, the more it stretches out. Right? Until it starts stretching the other way and pulls back in. Right? Okay, so let's set b back to 1. Now, c and d are your shifts. They move you left, right, up, down. C moves you left and right. Right now I have it set at 0, but if I start moving this thing around, and you notice when I move c in the positive direction, the function moves in the negative direction. If I move in the negative direction, the function moves in the positive direction. So this is also a way to manipulate this thing. And then lastly, D, that's your up and down shift. So you can translate this thing up and down like this. Just by, if you make D bigger, it goes up. If you make D smaller, it goes down. This one follows exactly what you would think it would do, just like A does. But C and B do weird things. They kind of behave in an opposite manner to what you would expect. So let's go ahead and get into how to handle some of these things. Okay, so looking at the last function we just looked at, right, the demonstration I just put up, basically what we were looking at, what I was trying to draw or write on here that didn't really come out the way I wanted, was that this function is set up so we have a sine of bx plus c plus d. Okay, so there's a bunch of stuff in here. Now, a is the amplitude, right? Or actually the absolute value of a is amplitude. And we've already looked at that. That's stretching it in a vertical fashion, right? You're making the peaks and the troughs higher and the peaks higher and the troughs deeper. Okay, now B controls your period. Now, the period is not whatever B is, though. The period is 2 pi divided by B, right? So that's your period. And the period, normally the period is 2 pi. So depending on what you do with B, it could shrink the period. So you finish a full, well, I was going to say revolution, but I haven't really talked too much about that part. But a full cycle of sine in a shorter period is what happens. And then C, well, that has to do with B also. C divided by B is your phase shift. And that's a horizontal shift. That moves you left and right is what it ends up doing. And the reason that it's C over B, and this is going to be something that we do fairly often here. In fact, one of the techniques for graphing I'm going to show you has to do with pulling out this middle piece here. If I have bx plus c, and I factor out the b, right? You notice there's no b here with the c, but if I can still factor it out. If I factor out a b, it's b times x, gives me bx. And then if I want to get c back, I have to have c over b here. And that's your phase shift, right? That's the guy, depending on if it's positive or negative. If it's negative, it moves to the right. If it's positive, it moves to the left. So I want to start taking some of these things and actually using them to graph. And I'm going to isolate them one at a time, and then we'll look at an example of everything at the same time. Okay, now, well, actually, before I do that, I do want to mention that the exact same rules hold true for cosine as well. The general form of cosine is f of x is equal to a cosine bx plus c plus d also. And A, B, C, and D do all the exact same things. Okay, so let's go ahead and clear this off. And we'll take a look at one of these. Okay. So let's say I have, in fact, let me draw across here. F of x is equal to sine of 2x. Okay, so we need to see what happens to the period. Okay, so the period, remember, is 2 pi divided by b. Okay, so the question is, what's b here? Well, if we look at the form, basically what this is, it's c is 0 and b is 2. Right, so b is 2 in this case. So my period is going to be 2 pi over 2. So it's the coefficient of x that you're really dividing by, which ends up being pi. Okay, so if that ends up being pi, that tells us that is as far as our graph needs to go, is up to pi. So let's go ahead and draw our graph. And the amplitude is still 1. I have a 1 out here. So that still plays in the way it did before. So this is 1, this is -1. And now our period is pi. Now, you need to do all the same things. You need to divide it down into quarters, just like we did with the basic sine function. So that means I need the halfway point, which would be pi over 2. Half of that, which is pi over 4. And then over here would be 3 pi over 4. Now, if you think about this, pi is now the unit. I have 1/4 of the unit, 1/2 of the unit, 3/4 of the unit, and then the whole unit. So I have 1/4 of pi, 1/2 of pi, 3/4 of pi, and then pi. Right? So it really is, it's just counting by fractions. You're counting by quarters in this case. Right? And it's a sine function. It hasn't been flipped. We don't have any negatives in there. There are no other constants. So that's the only thing that's changed, which means that now my graph, instead of going from 0 to 2 pi, goes from 0 to pi. So it goes up here to 1, back down to 0, back down to -1, and then up to 0. And it's a good idea, even though it doesn't always show up when you graph it, it's a good idea to get in the habit of writing those arrows on the end so that you know it continues, right? It doesn't just stop where you see it. But yeah, we have now altered the period of a sine function. Okay, so here's what I want to do here. Let's see. Let's go ahead and clear this off. And we'll try the exact same thing with cosine. Let's see how you do. So let's turn the pen back on. Let's say we have f of x is equal to cosine. Oh, let's see, what can we do here? Yeah, I don't want to go that direction just yet. Yeah, let's make it cosine of 4x. Okay, so go ahead and pause here. Figure out what the period is. Figure out how to break it into quarters. And then graph your cosine. So go ahead and pause it. Are you pausing it? Okay. Let's go ahead and take a look now. So let's see, we have to figure out what the period is. I notice my amplitude is 1. If the amplitude's 1, it's a standard cosine curve. The only constant we have in here is b, which means that the only thing changing is the period. So the period is 2 pi, it's always 2 pi, over 4, which is pi over 2. Okay, so now we have pi over 2 as a full period. So we're going to do the same thing. We're going to break this up. We know it goes all the way to pi over 2. So half of that would be pi over 4. Half of that would be pi over 8. And then here would be 3 pi over 8. So now that we have pi over 2, it'd be half of pi as a full period. If I break that into quarters, 1/4 of 1/2 is 1/8, which is where that 8 came from. And then I'm just counting by eighths. 2/8 is pi over 4, 3/8 is 3/8, 4/8 is pi over 2. So it's just counting along there. There we go. All right. Now, since that's the only thing that's changed, I know I can just go with the standard cosine curve now from -1 to 1. And that means it starts up here. We'll count down to here and then down to here, back up and to here. And it does continue, so we have to put the arrows on there, right? So that is one full period of cosine 4x. And that means it repeats 4 times in a period, in a distance of 2 pi. It's going to appear 4 times. And that's actually where this 4 times x plays in, right? It cuts the period into fourths. You could very easily cut the period into thirds or fifths or 196ths or whatever number you want to pick, right? They show up quite a lot. Okay, now, so let's go ahead and get rid of that. Okay, so now I want to introduce what happens with C, because what C does, C shifts you left and right is what it actually does. And so we want to take a look at that. So we've looked at what happens when the period is changed and it's shrunk down. And then we need to see what happens when we move it left and right. Okay, so let's see here. Let's look at f of x. Oh, let's turn on the pen. And then we'll look at f of x is equal to cosine x minus pi over 2. Okay, so we've shifted this by pi over 2. Now, here's the thing. This is minus pi over 2. Okay, minus pi over 2 means positive shift. It goes the opposite way you would think it would go. It's a positive shift, so that means it moves to the right. If it was a positive number, if it was plus pi over 2, then I would move it to the left, right? It actually goes the opposite direction you expect it to go. But this is essentially what happens. Normally, and I'll do this in two colors, normally cosine, let's see, there's no period change. Let's do this. Okay, let's put 2 pi here, and so that makes pi. So the period's not changing. So here's where we started. Normally does this, starts at 1, comes down, bottoms out at pi, comes back up to 3 pi over 2, and does this, right? That's the standard cosine curve. This has been shifted pi over 2 to the right. So what that does is it takes this point and just shoves it over to here. And so the curve, in fact, let's do this in purple. The curve starts here, and everybody moves over 1. Or moves over pi over 2, I should say. Right, so this would be 5 pi over 2. So we have to connect these dots. So I will start here at pi over 2, drive down to pi, bottom out here, come back up, and meet over here. So everybody has moved over exactly pi over 2 is what's happened. And if you want, you could actually continue this. And if you notice, when you continue it, it's actually the sine curve. Cosine of x minus pi over 2 is sine. Sine and cosine are the same curve, just set off by 90 degrees. That's the only difference. So it's kind of cool. And actually, if you look at the unit circle picture, the length of sine and the length of cosine are set to 90 degrees. They're 90 degrees off of each other because they form a 90-degree angle. So that's kind of interesting, I think. But yeah, so this would actually be the period that you're looking for. This guy right here, from pi over 2 down here and then back up and back up this way. And it does continue in both directions, right? So that's what you do. When you look at that phase shift, you look at what the sine is, and it moves that distance in the opposite direction of the sine. What's really happening is you're asking yourself, if you want to know what the shift is, it's x minus pi over 2, set it equal to 0, and whatever the solution is what your shift actually is. So if you add that over, you get x is equal to positive pi over 2, and that's your phase shift. That's actually how it works. And incidentally, that's why, remember in the formula I gave you at the beginning that I said the phase shift was C over B, right? Well, the reason for that is if I look at Bx plus C equals 0, actually it's negative C over B. Now that I'm looking at it, if we look at it and set it equal to 0, if I subtract the C over, I get Bx equals negative C, and dividing by B gives me x is equal to negative C over B. Right? So that ends up being your phase shift. So you notice that the phase shift was C was negative pi over 2. We had a positive shift, so the actual shift was positive pi over 2, right? And in this case, B was 1, so pi over 2 divided by 1 is still pi over 2, right? So now this little computation here, though, is going to save us some time later on, being able to do that thing with actual numbers in it. Okay, so let's go ahead and clear this off. Okay. Okay, so let's take a look at f of x equals sine 2x plus pi. Okay, so we got some stuff to do here. Now, if I just go ahead and factor out the 2, right, that gives me 2 times x plus pi over 2. Okay, so if you go ahead and factor that out first, that gives you two things. The 2 is b. It's what changes the period, right? So that means that my period is equal to 2 pi over 2. Or those 2's cancel, so the period is pi. Now, my phase shift, since I've already factored out this 2, right, that actually helps a great deal because that makes this right here, that makes this quantity C over B, right? And so my phase shift is the opposite of this. So it's negative pi over 2. So I have a period of pi and a phase shift of negative pi over 2. Let's see if we can piece this together. It's a sine curve. One of the things that is useful is to graph the original first. So let's do from 1 to negative 1. And then we'll just go ahead and do this. So we have, that's 2 pi, pi over 2, and 3 pi over 2. Okay, so those are my main things now. So first, let's go ahead and graph sine. So sine goes up this way to 1, goes back down to 0 here at pi, goes down to negative 1 at 3 pi over 2, and back up to 0 at 2 pi. Right? So it looks something like this. Now, the period change of changing it to pi takes that whole thing and cramps everybody down into this period of pi here. So that means that it goes up, down to pi over 2. In fact, this is what we graphed this last time, if you remember, when we did the period change. This is just a little more compressed. So it took the big curve in black and compressed it down to the small curve in blue. Then we have to apply the phase shift, which means I move pi over 2 in the negative direction. So let's look at what's at pi over 2. It's right here. That means that's sliding pi over 2 this way to 0. So that means this curve goes, let's just do that. This curve goes all the way down to negative 1 here, back up this way, and it follows in the reverse order. So by shifting it, we actually took the negative of it, right? So it ends up looking something like this. Or if you want to do the full shift and look at that same period that you moved, that moved over there. This, let's see, this would put the hump over here. and that goes to negative pi over 2. Right? So it's just shifting things around. So first we compressed it, then we moved it over. Well, actually moved it over. Right? That's essentially what we did. So my final curve ends up being the one in purple here. Right? This curve right here is this curve, the blue, it's the blue curve shifted over, right? So it went that way on each point and became the purple one. Okay, so that was a lot of stuff there. And this kind of gets messy sometimes. There's actually a nicer way to piece some of this stuff together. So I want to take a look at the exact same thing, but I want to do it in a slightly different way. So let's see if I can erase this. This is a much more mechanical way to get a hold of these things. But here's what a lot of people do. And we know that the key points we usually use for graphing sine and cosine are 0, pi over 2, pi. I'm going to run out of room if I keep doing this. Let's do that for now. Okay. 3 pi over 2 and 2 pi. Right? Those are my guys. So what I'm going to do is I'm going to take this, and one of the ways we can find the new graphing points is to take the argument of sine, and the argument is whatever you put inside of the sine function, and one at a time set it equal to each one of these constants and solve it for x. Those will be the new places that our key points have moved to. So the first point would be setting 2x plus pi equal to 0. Right? So that's the first one here. If I subtract pi over, I get 2x equals negative pi, and then dividing by 2 gives me x is equal to negative pi over 2. Over here, I have, in fact, let me just do this. So where do I want it? I'm going to keep a running total of the answers we get here. So negative pi over 2. Right? And then here, if I take pi over 2 and set it equal, 2x plus pi is equal to pi over 2. Well, if I subtract pi, that makes it negative. It makes it negative pi over 2. So that gives me 2x is equal to negative pi over 2. And if I divide by 2, I get x is equal to negative pi over 4. Now, let's start separating these. If I'm looking at pi, 2x plus pi equals pi. I'm going to run out of room here real quick. If I subtract pi, I get 2x equals 0. So x equals 0 here. So let's see, we have negative pi over 2, negative pi over 4. We just found 0. Now we need to do negative 3 pi over 2. So it's 2x plus pi equals, where was it, 3 pi over 2. I'm running out of room real fast here. Okay, if I subtract pi, I get 2x is equal to, let's see here, if I subtract pi, pi over 2. So dividing by 2 gives me x is equal to pi over 4. That's positive now. You notice these numbers are symmetric around 0. So the prediction would be that for 2 pi, we should get pi over 2 because we got negative pi over 2 on the negative end. Let's see. So it's 2x plus pi equals 2 pi. Subtracting pi gives me 2x is equal to pi, and dividing by 2 gives me x is equal to pi over 2. Okay, so the last one is pi over 2. Okay, so those are my key points now. So basically, all of those places where the sine curve was significant, where it started at 0, goes up to 1, back down to 0, down to -1, back up to 0. Those things happen at these points now. So when x is negative pi over 2, sine is 0. When x is negative pi over 4, sine is 1. 0 is 0. So it just moves right along. I'm going to go ahead and erase this part here over on the right. And then we'll just go ahead and get rid of that. And we'll graph this thing. So this is how we use those points now. So I need to make sure my graph is big enough for all of them to fit. So let's see here. I'll do negative pi over 2 here. Negative pi over 4, 0, pi over 4, and pi over 2. So I have those points now. That means sine starts here. Oh, let's give it a 1 and a -1. Goes up to 1 at pi over 4, right? So it tops out here and then comes back down. Ugh. I don't know, my hand's doing this stuff. Let's try this again. Right, and then back down here to negative. That shouldn't be a straight line, but you get the idea. Should be much more rounded than that, but yeah, that's basically what the original sine curve has turned into. It shrunk down and then it scooted over, right? That's the idea. Okay, yeah, and keep in mind that this thing started out over here, right? And if you look at the last graph, this is still the same thing that we had in the last graph. Right? It started at negative pi over 2. If you go back and look, you can see it. Peaked out at negative pi over 4, hit 0, back down to -1 at pi over 4, and then up to 0 at pi over 2. Right? So now these take some practice to get used to. But I think setting the argument equal to 0, pi over 2, pi, 3 pi over 2, and 2 pi tells you where all those key points are. So it tells you this point, this point, this point, this point, and this point. Right? So it's a good technique to use. Okay, so here's what I want to do. I'm going to give you another one, and I want you to try this one, and then we'll graph it together. Okay, so let's say f of x is equal to cosine of, let's make this interesting, negative 2x minus pi over 2. Okay, so let's see what you can do with that. Go ahead and pause it and see what you can get. And then we'll take a look and see how it actually pans out. There's a lot of negatives in that, aren't there? Okay, so again, we want to do this. We want to figure out where our 0, pi over 2, 3 pi, 3 pi over 2, and 2 pi go. So we're going to do this one at a time. This time I'm not going to try to space it out. I'm just going to go through them. So the first thing we want to set it equal to is 0. So negative 2x minus pi over 2 is 0. So I'll add the pi over 2. And if I divide by negative 2 here, I get x is equal to negative pi over 4. Okay, so that's my first point. So negative pi over 4 is where I'm going to start this graph. Then, so we got that first one here, setting it equal to 0. Next thing up is pi over 2. So we have negative 2x minus pi over 2 is equal to pi over 2. Well, subtracting or adding, I guess I'd be adding pi over 2 to both sides. So that makes it pi. So it's negative 2x is equal to pi. If I divide by negative 2, I get x is equal to negative pi over 2. Okay. And then Oh, this is interesting, the order things are going in, because this one started out as 0. Then when we had pi over 2, it went to negative pi over 2. Now we're going to do pi. So we have negative 2x minus pi over 2 is equal to pi. So let's see here. If I go ahead and add pi over 2 to both sides, I get negative 2x is equal to 3 pi over 2. And we're going to divide by negative 2, so that gives me x is equal to negative 3 pi over 4. Right? Okay, so pi went to negative 3 pi over 4. You notice these things, as this is a reflection, because these things are getting bigger, but these things are getting smaller. So these are moving to the right. These are moving to the left now. This is actually important that we keep these things lined up like this. So we got 3 pi over 4 there. Now we need to do 3 pi over 2. Right? So let's see here. We got negative pi over 4, negative pi over 2, negative 3 pi over 2, or over 4. Now we need to set it to negative 2x minus pi over 2 is equal to, let's see here, that would be, yes, 3 pi over 2. So if I add pi over 2, that makes it 4 pi over 2, which is 2 pi. Wait, I'll just write it down first. Right, if I throw another pi over 2 in here, this ends up being 2 pi. And then if I divide by negative 2, I get x is equal to negative pi. Right, so that means 3 pi over 2 went to negative pi. And the last one we need to do now is 2 pi. So I have negative 2x minus pi over 2 is equal to 2 pi. So if I subtract pi over 2 from 2 pi, I get negative 2x is equal to 3 pi over 2. Oh, I'm not subtracting. What am I doing? I'm adding. I'd be adding 2 pi. So that makes it 5 pi over 2. And then I would divide by negative 2, which gives me x is equal to negative 5 pi over 4. So 2 pi ended up going to negative 5 pi over 4. Okay, so that's a lot of computation, and I did kind of rush through a little bit of it. So some of that stuff you're going to have to go back and convince yourself that those are the answers by filling in some of the steps, and that's okay. There's nothing wrong with that, and it's a good exercise. In fact, when you read most math papers, they just kind of say the thing and say the conclusion and leave the rest as an exercise to the reader. So I'm not making excuses here. I think it's actually a good exercise to work some of those details out for yourself. Okay, and then let's get this off here. I think that'll do it. And we can go delete. All right, now let's go ahead and graph this thing. Now this is kind of interesting because these are going to be my points, but they run backwards. And we'll see as I graph this that they run backwards. So normally, oh, that wasn't any good. There we go. I need to go this way. Normally we would start at 0 and count this way. But in this case, because we're starting at negative pi over 4 and go all the way up to 5 pi over 4, let's go ahead and mark this. So let's say this is negative 2 pi. Oh, wait. Negative pi. Okay, so negative 5 pi over 4 would be here. And then, yeah, this would be negative pi over 2. And then this would be negative pi over 4. And this would be negative 3 pi over 4. Okay, so let's just graph these one at a time. So this is a, oh crap, was this cosine or sine? I should have left it on there. I want to say it was cosine. I'm going to go with cosine. Yeah, so let me go ahead and get this off here. Okay, so if it's cosine, that means we're still trapped between 1 and -1. So what would normally be at 0 is here. So that's up here at 1. And then at -π/2, we come down to 0. And then -3π/4, we're at -1. And then at -π, we're back up to 0. And then back up here again. And so I end up with these points. And even if you had graphed this backwards, like if you had started here and graphed the other way, you still get the same, you still get the exact same curve, right? It doesn't change anything. And if you continued this, it would keep moving down, and it would just continue to follow this cosine pattern, right? Okay, excellent. Okay, so that wraps up the high points. Now, I want to point out too that we are actually not done with this section. We had one lecture introducing the graphs of sine and cosine, just getting used to what the basic graphs look like, and then we played around with the amplitude a little bit. This time, we looked at how to modify the period and the phase shift, and went through that. Um, Now, we still do have a little bit more to cover on this. This video is getting a little bit on the long side, and so I decided to go ahead and end it here. We've covered all the main stuff. We haven't talked about D. D is pretty straightforward. It's a lot like the amplitude in that sense. It doesn't require a bunch of computation like B and C often do. So what we're going to be looking at next time is we'll look at a brief example of how to use D, although some of you may be able to figure that out on your own anyways. Um, and then we're going to start applying this to things and seeing how functions of sine and cosine actually get used. And that's more what I'm interested about, because it doesn't matter how much mathematics you know. If you don't know how to use it to do something useful, it doesn't matter if you know it or not. You might as well just be a trivia guy, right? It doesn't really help to know something if you don't know how to use it. It's like owning a car but not being able to drive it. It's the same kind of deal. So, in any case, we will wrap this up in the next lecture, which at this point looks like it probably won't be till next week, but we'll see. And until then, keep your pencils and your wits sharp.